dear student friends. Now we are going to discuss the concept aromaticity in this session. Concept is subject for the discussion now is aromaticity. We can also use another word, aromaticity, or simply this is called as Huckel's rule. Let us discuss this particular topic in this class, aromaticity or Huckel's rule. Yes. This word aromaticity refers to a unique property of all types of aromatic compounds. All aromatic compounds exhibits unique property. A special property is there which is associated with all aromatic compounds. We know very well that aromatic compounds usually contains double and single bonds alternatively in a cyclic structure and resemble benzene in chemical behavior. I repeat, aromatic compounds usually contains double and single bonds alternatively in alternate position in a cyclic structure that resemble benzene with respect to chemical properties. What are the properties we expect in benzene? The property is aromatic electrophilic substitution reaction. That is, substitution reaction is there. Substitution reaction is very easy to carry out in benzene rather than your addition reactions. This particular substitution reaction we can expect in all aromatic compounds. And apart from this, there is double and single bond in alternate position. This double and single bond position is there in cyclic structure in all aromatic compounds. This particular characteristic behavior is called aromatic character or simply aromaticity. Aromaticity reflects the presence of double and single bonds in a cyclic structure. That cyclic structure exhibits then the property equal to benzene, properties equal to benzene. This particular property, the benzene property, is nothing but a substitution reaction. It will not undergo addition reaction. This particular property is called aromaticity or simply aromatic character. And apart from this, to confirm this aromaticity, that is aromatic character, we have a simple method in lab. As I told you in my all classes, simply the given suspected aromatic compound is taken in a spatula and introduced into your Bunsen flame. That will catch immediately fire if it is aromatic. Say for example, take the case of your camphor. We used to show this camphor before the idol, before the statue, before the god's statue. What will happen when we ignite this camphor? Just imagine. It will catch fire and start burning smoothly with a lot of smoke, with a lot of carbon. You can see here and there flowing in the atmosphere, that is in the air. That is your sooty flame. So all aromatic compounds catch fire and burns with a lot of flame, lot of carbon, lot of your dust, lot of carbon, and in turn this is called your sooty flame. Once the compound burns and gives you a lot of carbon, that compound is called aromatic compound. One of the criteria to confirm the aromaticity as far as the laboratory is concerned. Apart from this, we have theoretically, we have, as I said, there is a double bond and triple bond. There is a double and single bond in alternate position. Usually aromatic compounds are cyclic structure bond. This particular behavior is called aromatic character or aromaticity. Or simply we can define aromaticity is nothing but the property of sp2 hybridized planar rings. Property of sp2 hybridized planar rings in which the p orbitals allow the delocalization of pi electrons. I repeat, this is property of sp2 hybridized p orbitals. As far as the aromatic system is concerned, all the atoms concerned with the aromatic system must have p orbitals, That p orbitals must overlap with one another and thereby allowing the delocalization of pi electrons. All aromatic system must contain. There is a rule to confirm how many electrons should be there for an aromatic compound to exhibit the aromaticity. That rule is nothing but your Huckel's rule, that is otherwise called the 4n plus 2 rule, where n is an integer, starts with 0, 0, 1, 2, 3, etc. etc. So the minimum electron required to exhibit the aromatic property is, say for example, if we consider the case as benzene equal to 6. So 6 electrons are there in benzene. As far as the benzene is concerned, there are 6 carbon atoms. Each carbon we can see the pi electrons. All the carbon have pi electrons that allow the pi orbitals. Pi orbitals. That pi orbitals in turn overlap because of the perpendicular position. This overlap with one another gives you the pi molecular orbital in which each carbon atom have one electron in the p orbital, that is hybridized orbital, so that will start moving, that will start delocalizing inside your benzene ring. That in turn gives you stability into the benzene. That is one of the unique property of benzene, where you find the delocalization of pi electrons. Not only in benzene, almost all aromatic compounds. All aromatic compounds we have a delocalization of pi electrons. This is because of the adjacent p orbitals overlap with one another, gives you the pi molecular orbitals. And now the discussion is, what are the criterion we have to confirm the aromaticity? We have 3 different rules to confirm. Under the criteria to confirm the aromaticity, we have 3 different rules. Rule number 1, and we have rule number 2, and we have rule number 3. I'll tell you what is what. In rule number 1, the rule number 1 says that, rule number 1 says that aromatic compounds are usually cyclic and planar. All aromatic systems are cyclic in nature and planar. Also planar. It is position to planar. The position wise it is planar and structure wise it is cyclic. This is rule number 1, and that is planar and cyclic. Planar and cyclic. And as far as the rule number 2 is concerned, each atom in an aromatic ring has a p orbital. As I said, each atom gives you, each atom that what we have in the aromatic system has p orbital. These p orbitals must be parallel so that continuous overlap is possible around the ring. This I have explained just before. Each atom what we have in the aromatic system. Say for example, take the case of benzene. There are 6 carbon atoms. So each carbon atom must have a p orbital parallel to one another. All the p carbons we have, in all the carbons we have a p orbital which is parallel to one another, so that the overlap is easy between the p orbital, between the hybridized orbitals of carbon of your benzene. And as a result, that when there is a overlap, and the next thing is, since we have 6 pi electrons inside the benzene, each carbon we have 1 electron in the hybridized orbital, and since there is a overlap, all the 6 electrons can feel easy to revolve inside the benzene ring continuously and smoothly. This is rule number 2. Now come to rule number 3. Rule number 3 says that cyclic molecular orbital that contain the electrons must contain 4n plus 2 pi electrons. This is your Huckel's law. The rule says that the p orbitals what we have in an aromatic system must contain the pi electrons that should obey the rule called Huckel's rule. That rule is nothing but your 4n plus 2 rule. 4n plus 2 rule. Rule number 3 is Huckel's rule must be obeyed. Huckel's rule has the aromatic system must have to obey, should have to obey. Rule number 2, overlap should be there. Overlapping leads to the formation of pi molecular orbital should be there as far as rule number 2 is concerned. Rule number 3 says that the Huckel's rule, that is your 4n plus 2 rule should have to obey by the aromatic system, where n is an integer that starts sometimes 0, 1, 2, 3, etc. etc. So regarding the criteria, as I said, there are three criteria. Criteria number 1, aromatic system must have pair, that is planar and cyclic. Rule number 2 says that aromatics in all the atoms concerned in the aromatic system must have the p orbital overlapping, the position wise that should be parallel to one another, so that smooth overlapping, thereby allowing the pi electrons what we have in the aromatic system for its delocalization is possible as far as rule number 2 is concerned. Rule number 3 says that the aromatic system, the aromatic compound, suspected compound, should obey the rules called Huckel's rule, and the rule is nothing but your 4n plus 2 rule, where n is an integer, sometimes 0, 1, sometimes 2, and 3, etc. etc. Now we are going to discuss in detail by applying this Huckel's rule one by one. So for example, we are taking the Huckel's rule. We are going to apply the Huckel's rule with respect to benzene first, whether the benzene is obeying the Huckel's rule or not. So based on rule number 3, if the suspected compound should if it should exhibit the aromatic property, that should obey Huckel's rule. So with the help of Huckel's rule, one can decide or one can confirm, one can easily infer whether the given suspected compound is aromatic or aliphatic, theoretically applying Huckel's rule. Yes. Now take the case of benzene and try the benzene using the Huckel's rule. Now remember, you are going to apply the Huckel's rule into your benzene. You are applying benzene to Huckel's rule. You know that the structure wise benzene is planar and cyclic also. This is planar and cyclic. So rule number 1 is satisfied. Planar and cyclic. Rule number 1. And rule number 2 says that each atom of the aromatic system should have the p orbitals sufficiently position-wise parallel to one another, and apart from this, each orbital must have one free electron. That is also there as far as the benzene is concerned. We have a p orbital, each contain one electron, and as a result there is a smooth overlapping is there, and because of the overlap, delocalization of pi electron is possible according to rule number 2. Now come to rule number 3. Both the rule number 1 and 2 is applied perfectly, and now we are going to apply rule number 3, that is your 4n plus 2 rule. 4 remain 4, n 1 for benzene and 2 as such. Therefore the result is 4 plus 2 rule is equal to 6. This is nothing but number of pi electrons. So 6 pi electrons should be there in benzene. I'm drawing the benzene again. This is 2 pi electron. This is 2 pi electron. 2 pi electron. 2 plus 2 plus 2 is equal to 6. So 6 pi electron is there according to your Huckel's rule. So naturally the benzene is aromatic, exhibit the property called substitution reaction. Chemically, it undergoes substitution reaction very easily compared to your addition reaction, one of the important property of your aromatic compounds. So as far as benzene is concerned, it obeys rule number 1, rule number 2 and rule number 3 also perfectly. Therefore, without any doubt, benzene is an aromatic compound. Now, take the benzene little in a spatula introduced in your Bunsen flame in the laboratory. It will catch fire and burns with a sooty flame. Again, practically you are confirming the given benzene is aromatic. Now come to the next one. Next is cycloheptatetraene. Cycloheptatetraene. The structure is this. 1, 2, 3, 4, 5, 6 and 7. Yes. This is your cycloheptatetraene. We have 1E, 2E, 3. Therefore, this is a triene. If you apply this into aromatic, that is the criterion, all the 3, in particular, try to apply this in Huckel's rule. 4n plus 2. 1 plus 2 should be 6. Of course, here also 6 electrons are there. 2, 2, 2. And apart from this, though we have 6 pi electrons in cycloheptatetraene, the delocalization, the pi molecular orbital, the p orbitals of cycloheptatetraene, the overlapping is not there in all the atoms concerned. Here we have a pi electron, no doubt. Here we have, 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 and here there is no p electron, there is no pi electron, there is no p orbital, there is no p orbital because this carbon is saturated. There is no p orbital. Here we have p orbital. In all the 5 atoms of cycloheptatetraene, we have p, that is pi orbital. Whereas in 6th position, there is no pi orbital. Only when there is a pi, the rule number 2 says that all the atoms concerned in with respect to the aromatic system should contribute 1 pi orbital, one p orbital for smooth overlapping. Here there is no p orbital, there is no p orbital in position number 6. As a result, there is no smooth overlapping, and ultimately there is no delocalization of pi electrons possible, and the result is non-aromatic. Therefore, the compound cycloheptatetraene is your non-aromatic system. See the board. So, to confirm whether the given compound is aromatic or aliphatic, we have to follow 3 important criteria. Number 1, system should be planar and cyclic. Number 2, all the atoms concerned in the aromatic system must have a p orbital, and the position wise all should be parallel to one another so that easy overlap should be there. And when there is overlap, according to rule number 3, the enough pi electrons, say for example take minimum 6 for n plus 2, if n is 1, the 6 pi electrons start delocalizing easily inside your aromatic system, ultimately gives you the stability to the aromatic system. This is the reason why the aromatic systems are highly stable. The delocalization of pi electrons inside your aromatic system gives you the stability to the cyclic structure. With this, we are closing the discussion now. We'll try to discuss the same topic in the next session also, by applying some more aromatic systems and plus non-aromatic systems. Thanks for watching this video. Thank you.